In this lesson, we're going to talk about how to rationalize the denominator. But before I start telling you how to do that, let me tell you what rationalizing means and why it's necessary. And so let's get started by talking about what are rational numbers. Well, a rational number is one that can be written in a fraction form. You know, the root part of rational is ratio, and ratio means fraction. So if it can be written in a fractional form, it's called a rational number. Not all numbers can be written in fraction form, and a really famous example of that would be pi, which, you know, has never-ending decimal places and cannot be represented in a fraction form exactly, and so pi is irrational. And all of our square roots that cannot be simplified into whole numbers, they're all irrational. And so why does it matter if a denominator is rational or not? Well, since irrational numbers have never-ending decimal places, it's really hard to do long division with irrational numbers. So like, think about if you were a mathematician way back when, or a scientist way back when, and you had to divide by some irrational number. For example, just for a simple example, 5 divided by square root of 2. Well, you would first have to come up with a decimal approximation for square root of 2, which might be, you know, it's approximately 1.41421, and you might round that off and not need all those decimal places. But suppose you had to do, for some reason by hand, 5 divided by 1.41421. Well, this is a really messy prospect. It's going to take a lot more room than I have here, and it's going to take quite a bit of time as well, because you know that the more digits you have out here, the nastier this process gets. Okay? So this is hard, and we do not want to do it. Nobody ever wanted to do this. So what they did was they developed a process called rationalizing that makes that bottom number a whole number instead of an irrational number. So one thing we could do is we could multiply this denominator by something that would make it a whole number. Now with square roots it's easy to figure out what that is, because a radical times itself gives you the number that's under the radical. So if we multiply the top and the bottom both by square root of 2, then in the top we get 5 times square root of 2, like this. But in the bottom, square root of 2 times square root of 2 is 2. And what we've effectively done is we've moved the radical, the irrational part, from the bottom to the top. But pretend again that you're an old, you know, way back when scientist or mathematician, and that you've got to actually come up with this decimal number. So what you would have to do in this case is, remember we already said square root of 2 is approximately equal to 1.41421. Well, you would have to do 5 times 1.41421, and you would get this with no trouble at all. And then you would have to divide that number by 2. Now because we're dividing by 2, it's really no trouble because we've only got one digit out here, so that's pretty easy. And even though it took a little bit of room, it wasn't a difficult or time-consuming process. So we end up with 3.535525, just to, you know, to so many decimal places. And this was a lot easier because we were able to divide with just one digit out here. So if you're a mathematician back in the day, which are you going to choose? The division where you have 6 or 7 digits outside here, or just one digit? You'd a lot rather have one digit. So that's why rationalizing was considered a good thing. But now we know now that this 5 over square root of 2 is equal to 5 square root of 2 over 2, and this one is preferred because if you have to work by hand, this one's easier to deal with. The irrational number in the top is easier to handle than the irrational number in the bottom. Okay. And we see just again that denominator is rational, and that's what makes this form nicer than the other form. Okay. Now, we will not be concerned with the long division. We are not mathematicians and scientists back in the 19th century. We're in the 21st century, of course, and we have our handheld calculators to help us out. And so we kind of don't care as much as they did about the irrational numbers in the denominator, but still it's just a form, it's just a common courtesy type of thing to leave the denominator in a rational form. So we're not going to be working them out in decimal form, but all we're concerned about is learning how to write fractions where they have a rational denominator. So let's practice this one. Rationalize 7 over square root of 3. So you remember that rationalizing just means getting rid of the radical in the denominator. And we know that if we multiply this radical times itself, we'll get rid of the radical in the answer, but we know if we do it to the denominator, we have to do it to the top. So it becomes 7 square root of 3 over 3. And the end goal is accomplished, which is no radical in the denominator. So as long as we have just a single radical in the denominator, it's very easy. We multiply the top and the bottom of the fraction by that same radical and reduce if necessary. And I've got some examples here on the next page for us. So let's do 7 divided by the square root of 5. And this is just a single radical. So we'll do square root of 5 over itself. And that will give us 7 times the square root of 5 over 5, because square root of 5 times itself is just 5. Now 7 over 5 cannot be reduced, and the square root of 5 is a radical that cannot be reduced, so this one is finished. And here's another one. 6 over the square root of 12. Now, if you think about it, there are two things that need to happen here. For one, this radical needs to be simplified. 12 contains a perfect square factor, which is 4, so this radical can be reduced. But also the denominator must be rationalized. And it doesn't really matter whether you rationalize first and then reduce the fraction, or whether you reduce the radical first and then rationalize. It's totally up to you. In this case, I am going to multiply by square root of 12 over square root of 12 and rationalize first. So I'm going to end up with 6 square root of 12 over 12. And then 6 over 12 reduces to 1 over 2. And the only thing left for me to do is reduce this radical. 12 is 4 times 3, and the square root of 4 is 2. And that leaves the 3 under the radical. And then here I'm going to reduce the fraction again. 2 over 2 is 1. So I'm left here with just square root of 3. And again, you can simplify the radical first, or you can rationalize first. It does not matter. Okay, 15 over square root of 6. Let's rationalize. So we're going to get 15 square root of 6. And in the denominator, square root of 6 times itself gives us 6. This radical cannot be reduced. However, 15 over 6, both of these numbers can be divided by 3. So that will leave us with 5 square root of 6 over 2. Alright, last part for this page. 12 over square root of 8. I'm going to rationalize first. And that's going to give us 12 square root of 8 in the top and 8 in the denominator. So now it's rationalized, it just needs to be reduced. 12 over 8 will reduce to 3 over 2, because both of those numbers can divide by 4. Now 8 becomes 4 times 2. The square root of 4 is 2. So I'll have a 2 outside the radical here. See, my square root of 8 simplified to what's in red here. Now those 2's will reduce, and all I get left with is 3 square root of 2. Now we're going to look at rationalizing with 2 terms in the denominator. So here is an example. 6 over 7 minus square root of 2. And I just want you to see that if we try to do what we've been doing and we multiply the top and the bottom by square root of 2, it won't help, because 6 times square root of 2, of course, is that, but if I multiply square root of 2 times both of these terms, I still have a radical in the denominator. So this method is not going to work on this type of problem with two terms in the denominator. And we're going to need a new way to eliminate radicals if we have two terms. So think about this. Now look at the denominator I had, 7 minus square root of 2, and let's multiply it by what's called the conjugate. This is a conjugate when you have the same two terms but different signs in between. Now if you use the FOIL process on these, 7 times 7 is 49. Outer times outer is 7 square root of 2. Inner times inner is minus 7 square root of 2. And last times last is minus 2. Look at what happens to our radical terms when we do that. They are the same but opposite signs. So they go away, and all we're left with is 49 minus 2, which of course is 47. Okay? Now, that gets rid of the radical, which is really all we wanted in the first place. So I think multiplying a two-term denominator by its conjugate is going to do what we need to happen. So again, these are called conjugates, and multiplying conjugates together eliminates the radical. So if we go back to our original problem now, and we try to multiply the top and the bottom by that conjugate, watch what happens. I'll have to distribute the 6, so 6 times 7 will make 42, and 6 times this radical will make minus 6 square root of 2, and I've got a little typo there, so that needs to be a plus 6 square root of 2. Okay, in the denominator, 7 times 7 is 49. Then outer times outer and inner times inner we know go away. And then minus square root of 2 times plus square root of 2 is going to give us minus 2, just like it did before. And we're going to end up with 42 plus 6 square root of 2 in the top and 47 in the denominator. Okay, just for practice now, let's rationalize 5 over 9 plus square root of 7. So the first thing we do is we notice that this is two terms, so we'll have to multiply the top and the bottom by that conjugate, and then let's just do it. 5 times 9 is 45, and 5 times this radical is minus 5 square root of 7. Now in the denominator, remember it's FOIL method, so first times first is 81. Outer plus inner we're not even going to bother with, because we know that since these are conjugates, outer plus inner will add up to 0. Now last times last is going to make minus 7. And so we're going to have 81 minus 7 in the denominator, which is 74. Now one common source of mistakes here is a lot of people try to do the subtraction, the 45 minus 5. You cannot do that, because remember your order of operations. Multiplication comes first before subtraction, and we have a multiplication here. So this is not 45 minus 5. This is 45 minus this other product. And so since you don't know what 5 square root of 7 is, you can't complete that subtraction. Okay, another example, same type of problem. 8 over 4 plus square root of 5. So since our denominator has two terms, we will multiply the top and the bottom by the conjugate of that two-term denominator. So distributing the 8 here, 8 times 4 is 32, and 8 times square root of 5 is 8 square root of 5. Now in the denominator, 4 times 4 is 16, but it's not finished yet. Outer plus inner will add up to 0 because these are conjugates, and last times last is going to make minus 5. So we have 32 minus 8 square root of 5 in the top, and 16 minus 5 in the bottom, and 16 minus 5 is 11. So this one is finished. Since nothing else will simplify here, this one's finished. But just as a reminder, again, you cannot do this subtraction here, this 32 minus 8, and get 24 square root of 5, because this 8 is attached to this square root of 5. So you cannot treat this like subtraction first and then multiplication. Remember, multiplication always comes first before subtraction. So another way to think of it is that these are not like terms. The 8 square root of 5 is a different type of term from the 32. Now sometimes you may have to reduce the fraction after you rationalize, and so let's just look at one of those here. 6 over 8 plus square root of 2. Of course this is two terms, so we will rationalize it by multiplying top and bottom by the conjugate. Now let's distribute the 6. So 6 times 8 is 48, and 6 times square root of 2 is of course just that. Now 8 times 8 is 64, and outer plus inner will go away, but last times last is going to make minus 2. And we will simplify the bottom. 64 minus 2 is 62. Remember, we can't do this subtraction in the top. However, I do have 3 terms here, or I have 2 terms in the top, and I have my bottom factor. So since each of these is an even number, I can cancel a 2 from every term. And if I do 48 divided by 2, I get that. 6 divided by 2, I get 3. What's under the radical doesn't participate. It's just as if it were a variable. It doesn't change. And the bottom divided by 2 leaves us 31. Now, if you don't have anything that will go into all 3 numbers, then you know you're finished, as long as this radical can't be reduced here. And so that one is finished. Here's one more. Let's rationalize 5 over square root of 7 minus square root of 2. So again, it's 2 terms. It does not matter that this one has a radical. It's still 2 terms, so we still are going to treat it with a conjugate. And now let's distribute the 5 to both of the top terms, and let's multiply the bottoms together. Square root of 7 times square root of 7 is 7. Outer plus inner is going to add up to 0 because these are conjugates. And last times last is going to make minus 2. Now, I get 5 square root of 7 plus 5 square root of 2. So now notice that this coefficient and this coefficient and this coefficient all can be divided by 5. So let's do that. And when we do that, the denominator becomes a 1, which I did not write because we never write denominators if they are equal to 1. And so that's the end result of this one.